EE211 analog circuit design course. So we have discussed on various things on top of single stage amplifier, that the expected current source should have two characteristics. Mainly, the source impedance has to be infinity and the minimum voltage required for the current source has to be zero. But this is not going to happen. This is one of the ideal thing which can only happen on pen and paper, that we want this one. So I desired with respect to voltage should have such kind of characteristic. However, in reality, it will have different kind of things. So this minimum voltage will not be zero. It will have some finite value, and this resistance is actually the slope of this one is 1 by resistance. So we are expecting that the resistance is infinite. However, the resistance is infinite. However, it's not possible to achieve this slope equal to zero, right? So this is one of the crucial thing, and we have to devise some techniques through which we can have various kind of current source which are process voltage and temperature independent. One of the technique we have seen where two resistances are kept in ratio just to achieve what we want. So the bias potential, so this is actually the the ratio is there, R1 and R2, and V bias is actually deciding the current flowing through this transistor, right, as per the square law or the square law current equation. So in that case, we can move further. This was one of the technique. So you can see that the source of this particular figure is from Behzad Razavi. It's a blue colored book which I have used for this. So mainly, what is the role of current mirror? So generally, this is being used in the chip design. If you want everything on chip, and you want that there is some reference generator or the master current source, and all other are slaves. So you are deriving those currents from the reference current generator, then this will be very much important. What I mean to say is, let's assume that I'm generating PVT independent PVT independent I reference, let's say whose value is around 1 microampere. And in my circuit, there are many places where I need to have various currents like 2 microampere, 4 microampere, 6 microampere, 8 micro, or something multiple of 1 microampere. If I need to derive it, I can derive it through the simple circuit, which is the current mirror which we have just seen, or maybe with some different topology which we are going to study afterwards. But we have to make sure that whatever the configuration we are achieving, it should have two characteristics, that the source impedance is infinite and the minimum voltage is zero, or it's as low as zero, as high as infinite. This is what we want. We are not saying that it's always achievable, but we have to get some number. So source impedance might, we want to have as high as some mega ohms, and V minimum as low as some microvolts. So you can use many techniques, and where you can use enhancement mode transistor, you can use depleted mode transistors, and you can achieve what you want. So now let's go to the next slide, where there is another current mirror, where you can see that it's quite interesting that one of the side is created by a diode connected configuration, and another side is a normal current 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 sinks because the current is going inside. Same thing if you are designing with PMOS like this, then this is known as, like, let's assume that some current is flowing through here, and this W by L and this W by L of the transistors are same. Then for any given load, the current flowing through this one is also I, or identical to this I. By the way, this is giving the current to this load, so this is known as the current source. This configuration is current source, whereas in another configuration where there is load is given on top with respect to VDD, I have a transistor which is connected as follows. Then if both the W by L are same, then the current flowing through this branch and the current flowing through this one will be same. However, it's providing the current to this transistor or asking the current from here, then it's known as current sink. So that's the main difference between these two, where, like, what is the direction, it's going towards ground or coming from VDD. So accordingly you can say that it's a current source or current sink, and combining both of them it's known as current mirror, because we are using the current mirror configuration, or you are mirroring from one branch to the another branch, right? So let's assume that you have, like, the understanding of current source and current sinks are similar. However, we can stick to NMOS. Then let's assume that there are two transistors whose names are M1 and M2. This one has W1 by L1 and this one is W2 by L2. And if there is potential here, which is has to be VDS set. Now remember, as per our theory, VDS set has to be greater than or equal to 250 millivolt or sometimes 300 millivolts, so that you can achieve the transistor in the saturation mode of operation. And this side is also another VDS set, which is 2, belongs to 1, right? And this one is VGS 1 or VGS 2. Both are equal, and notably this is equal to VDS set 1 also, right? So these are the standard thing which we can understand. So now looking at the current flowing through each of the branch, if this current is I1, this current is I2, then I1 is nothing but mu n Cox by 2 W by L VGS minus VTH whole square. It's a square law. For the case of I2, mu n Cox by 2 W by L VGS minus VTH. But here the numbers are little bit changed, like VGS 2, this becomes VGS 1, this becomes W1 divided by L1, W2 divided by L2. And assuming the fact that all other device parameters are constant, then if you are taking the ratio of these two, then it's only depending on transistor sizing. Or you can say that if channel length is fixed to the minimum one, then it's only depending on the width, right? So if you want to have double of the current at I2 branch, then you should have the actually twice of W by L here than the W by L of first transistor. So this is going to give you the double current. If you want 3 times, then use 3 times. But notably, when we are doing this, the cadence, okay, I'm supposed to explain this also, that this is the tool which is used in every industry, known as Cadence Design Suite, and other are also there, like Eldo is also there from Mentor Graphics, but Cadence Virtuoso is used to simulate such kind of transistor. Generally, uh, like in IIT Mandi, we have almost like 50 licenses for the Cadence, for Virtuoso and other design suite. And so if you are using that, there are different parameters are given to you, and you have to feed them for the transistor. Like width, you need to write down in meter. You have to write down length in meter, and another one is called multiplier. So as I explain you that the transistor has to be matched just to get the exact current or the current in ratio. If you fix M1 to W1 by L1 transistor, and if you want the double of current, you need to keep this twice of W by W and L of the first transistor. So this is very important to do that. So if these are the first transistor's parameter where multiplier is 1, then in M2 you have to copy paste the whole thing. It has to be exactly same as M1. However, the only difference which is created here is the multiplier. If you need the current of 3 times, keep it 3. If you need the current of 4 times, 5 times, and so on. So you can keep n here. Sometimes it happens that you want the current as divide by some number, like, so then you have to keep here some bigger number. Let's say if this is 10, if I need the current divide by 10, then I can make it multiplier as 1. So this will be the divide by 10 current flowing through M2. So it's all about how you are fixing the multiplier. However, there is one more thing, it's known as fingers. So let's understand what is fingers mean. So generally transistor looking from top look like this one. Okay, this is the top view, but this is source, drain. By the way, these two are interchangeable, and this is gate, and body is the white part at the back is actually body. You need to create it, create the connection. So if there are two transistors in shunt, as we are doing in multiplier, so if I am doing this, where this is W by L, this is W by L, and this is, so this is source, this is drain, and this is gate. This is for the case when transistor width is or length are as follows. So if this is the case, like when we are saying that multiplier equal to 2 and width and L are actually given, so in that case that will make the schematic like this. So even though in cadence you are going to see only one transistor, sometimes you are keeping the this ratio as 100 also. So multiplier is 100,000, depends on the application, or sometimes like 1 also. So you are going to see only one transistor, but at the back when you are going to make the layout, you have to make this way, that those many transistors are in parallel. So this is the case of multiplier. However, there is another technique or another way of writing these parameters like width, length, and you choose not to bother about multiplier. Let's call it 1. And there is something called fingers. So there is something called finger. So finger is referring to the gate. So here also you can see that there are two gates are there which are tied together. Whereas in the case of fingers, it's similar structure. There are two, all the transistors are in parallel as happening here, but they are actually kept very much nearby, like this one. They are overlap. And when we are doing this, if you are saying that fingers are 2, then there is one more parameter which is getting activated, and it says that effective width per transistor. Note that when you are doing this, whatever the width you are giving here, this effective width per transistor becomes W divided by whatever the fingers you are giving. So if your width is 100 micrometer and fingers are 2, then width becomes, effective width becomes 50. So in that case, so this is for just for assumption, so f equal to 2, so then this becomes 50 micrometer of length, of width. So in that case, this becomes 50. And notably, another transistor which is in parallel, this is also 50 micro. So here, this is the major difference, that when you are taking this width becomes divided in the case of fingers, whereas in the case of previous example, multiplier actually keep those many transistors in parallel and increase the width with the multiplication. So the effective width per transistor here is 50 micro, and that one has 100 micro, right? So this is a purely how you are taking the multiplier finger. So generally in industry, people are following multiplier. The reason is, while taking the multiplier, if you take the cells from the library, which are known as P cells, if you're using this source, drain and gate, so if there is multiplier, you have to keep those many transistors in parallel. So this is what you have to do manually. So this is one transistor, this is another transistor, you have to keep both the transistors in shunt, the way we were doing earlier, like this. You have to treat them separately. So this is source, this is gate, and this is drain. So you need to short them accordingly. Whereas in the case of fingers, so as many number of fingers you have, you are going to have, let's assume that you are making for 2 fingers transistor, then it will look like this one, where it will take some overlap exactly on top of each other. So it will save the area sometimes. And if you do the calculation, that might be like a part of different course called layout, where if you are doing the layout, you will understand that effective parameters and area is actually reducing in the case of fingers. So in the case of multiplier, you have to keep those many transistors in parallel, and you have to keep it separately. So in that case, you are keeping some extra space also, so that like you can remove or you can add something at the end if you wish to do. So now let's understand one more thing, that there are various sources of errors when you are making the current mirror. Those are, the slope in the saturation region is not equal to 0. You want to make it 0, but it's not 0. Means channel and modulation is there, right? This is similar case when we are thinking about this particular configuration, where we were expecting to do following analysis, that, so this is NMOS, this is NMOS. So here if some current is flowing through this one, so for given load M1 and M2, so as we know that we need to evaluate this for two things, that what is V mean and what is source impedance. So looking at the output side, this V mean is nothing but VDS set. So this is the voltage which we are going to see. This will be around 250 to 300 millivolt, right? and the source impedance looking from here, which is at the drain of the transistor. So you are going to see R0. So R0 is the channel length modulation resistance, and this is directly depending on the second order effect, which is known as channel length modulation. And if you draw the characteristic required current with respect to VDS, you are going to see this kind of characteristic where this point is actually VDS set or the VDS set line, and this side you are going to have the slope of 1 by R0, right? So this is what you got, and this is the limitation of single transistor. As we talked about, there are sources of errors which is in associated with current mirrors are the slope and the voltages, which is not minimum, so that you can't avoid it. So minimum voltage will be there, and even slope wise, which is 1 by channel length modulation, that can be avoided by increasing the channel length. So here we always talk about W by L, and generally we don't touch channel length for the design of for the channel for the design of an amplifier or anything. Generally we keep L as minimum, but this is the fact only associated with digital circuits. For the case of analog circuits, we don't keep minimum L, and especially for the case of current mirrors, you need to keep L as 3 times of minimum L is required at least. This is a thumb rule, or it varies also. So, and if you are increasing more than 3, so afterwards the effect is almost negligible, so you are not going to see anything. So while doing this, you need to make sure that if you are multiplying this with 3 times, then width also has to be multiplied by 3 times, so that it's fix what we wanted. So if both are 3 times width divided by 3 times length and same other side, then the current flowing through both side are equal, and this R0 is going to get improved, and you are going to see the characteristic maybe like this. If the channel length is very high, or you can say that 3 times the minimum is required. So here you can reduce the channel length modulation parameter lambda. Okay, there is one more thing that is very difficult to say, that the potential across this one VDS1 or VDS1 set is equal to VDS set 2, although that is what expected. But this is one of the sources of error, where both side you are not going to have the same voltage because of the mismatch of this resistance, because looking from this side it's actually 1 by GM, and looking from drain side it's RO. So this is uh, sure that it's not going to be same. However, VGS1 and VGS2 will be always same, as they are tied together. So now one more thing is, like, V minimum is not 0. That is also one of the source. But in that case, we can't avoid it, because every transistor needs at least certain voltage of saturation voltage, or the VDS set value, which will make the transistor in saturation. So for that, I gave you one number. It has to be 250 millivolt to 300 millivolt. If you can achieve it, or more than that, you are in a safe zone of saturation, and things will work. However, you need to give the common mode or the DC voltage at that particular transistor. And as we understood about, the value of this VDS set is actually associated with the headroom. So as many number of transistors you can cascade it, if you understand common source goes to common gate. So those things we are going to study next phase of understanding, that what we can do next to achieve the better current mirror, or the better current source, or better current sink design. Still, our agenda is fixed. We want source impedance as infinite, and V minimum equal to 0. This is what we want. I'm repeating this because this is the only golden rule for making a good current source, a current sink or current source. So in that case, with one transistor topology, you have achieved R0, which is in the range of some kilo ohm, 1 kilo, 2 kilo ohm, maybe 10 kilo ohm, but not more than that. It's technology dependent. V minimum, we got something like VDS set, which is around 250 to 300 millivolt. So this is what we have achieved. So what next we can do, that we need to think. But before that, let's think about one example where we need to determine the overdrive voltage at the output of the current sink. So you can identify that this one is a current sink, where this is M1 and this is M2. So across this one, it will be VDS set, VDS2 set, referring to the second transistor. And this side, it's VDS1 set. Set is the one which is deciding that you are in saturation or the transistor is in saturation. By looking at all this theory, we also know that VDS set is nothing but VGS minus VTH. So VDS set has to be more than VGS minus VTH. This is what we studied also, that VDS set is higher than VGS minus VTH. So let's assume that we are at exactly at the age, and so if you are referring different books are following different kind of notations. They are also calling this VDS set as V on voltage, and this is same as what we are calling VGS and VTH. So if you are referring Alan Holberg book, which I am also following for the like rest of the lectures on current mirror, then they are following that VDS set is nothing but V on. So in that case, you can say that VGS is nothing but V on plus VTH. So let's understand this carefully, that V on, which is VDS set, is equal to VGS minus VTH. And from this equation, I'm saying that VGS is nothing but V on plus VTH. Or you can, if you want to write down VDS set, you can write down VDS set. Right? So if that is the case, let's look at one transistor. And I'm not going to write anything in terms of VGS. I'm going to write only in terms of V on or VTH, because that is what I like, because VDS is easy to handle. V on voltage, I know that it's 250 millivolt. Rather to find out VGS or VTH, which is technology dependent, let's talk about V on. Let's fix to all the equation to V on. So in that case, we know that this output is V on because it's VDS set, and gate to source potential is nothing but V on plus VTH. Look at this, like just I modify the equation here and there, but it's same. So if this is the case, you can say that if gate potential is available at whatever the potential, at drain side it will be subtracted with VTH, right? This is already this equation. So you can say that if gate to source is V on plus VTH, so this has to be subtracted, this quantity has to be subtracted with 1 VTH, which is going to give me V on. This is very simple and elegant way to look at the transistor, just to find out the minimum voltage range, right? Because we are expert of finding out the impedances, however we don't know how to find out the output voltage or the minimum voltage which is required for the current source or current sink design. So here I know that output is VDS set 2, or it's equal to V on 2. Let's name it V on 2. Let's name this one as V on 2 plus VTH. right? And similarly, like this VDS set has to be exactly equal to V on 2 plus VTH. You can rename this one also as V on 1, right? So you can derive VDS1 in terms of VDS2 and VDS2 in terms of VDS1 and so on. So this is one thing. So output voltage is V on 2, which is absolutely known to us, which is like as per my theory, it has to be like more than 250 or 300 millivolt, and you are into safe region of saturation. Now, the next thing is you have to see what is the impedance looking into this transistor, because we are here and we want to find out what is the impedance here. So that impedance looking at drain side of a transistor, we are going to see R0. So concluding this, determine the overdrive voltage. By the way, yeah, so there is one more thing. Some book like Razavi, they are writing this as V overdrive voltage also. But all are synonyms. You can write this one also, no problem. So this has been inspired from the book called Razavi, and that's why like I have written overdrive voltage. So overdrive voltage is equal to V on and is equal to VDS set, whichever you are using. So all are same. So in that case, like overdrive voltage is known to us, that is equal to VDS2 set or one overdrive voltage and V on 2. That is what we got here, right? Now determine the output impedance, that is known to us, that is equal to R0. So this is what we achieve, and this is what already known to us also. And as per our theory, this is the design which we are keeping here. That oh sorry, I went too much ahead. Yeah. So this design has different notation. They are not in terms of VGS and VTH, but they are in terms of actually VDS set. It has to be written VDS set, right? Or V overdrive voltage or the V on voltage. All are synonyms, as I told you, or overdrive voltage. All are synonym. So in that case, this design has been made. Now look at the different structure. Like like our agenda is to make a current source or current mirror with only two golden rule. That source impedance will be higher and V minimum will be 0. In the case of the first design, what we did it with the normal transistor, what we got, source impedance is equal to RO, which is in kilo ohm, and we got V minimum equal to V on or VDS set, which is also known to us 250 to 300 millivolt or maybe higher than this one, right? So this has been achieved. If you want to have this higher source impedance, what I can do, why why shouldn't I use the cascode load or the cascode topology and name it as a cascode current mirror? How does it look like? So if you're looking this, you have to stick to transistor one on top of another one. By the way, this current can be generated by a resistance also, and from the available voltage drop you can have the current, which is, if this is V1, VDD minus V1 divided by R is going to give you the current flowing through this one, right? Or I can call that one as the normal current whose value is I, right? So you can do this one. This looks very elegant. If this is M1, this is M2. If this is again M1, this is M2. The current flowing through both the branches will be exactly identical, right? Because this is following all the current equation and all. we are not going to go into detail again, because you have to just follow the current equation, which is the square law. If you take the ratio, you will find out that current flowing through this branch and this branch are same when the transistor ratios are equal, right? So as we know that we have found out this, but we need to evaluate it, whether this particular design is good or bad. For getting or evaluating this design, we need to check what is the source impedance and what is the V minimum voltage at the output. So looking into the source impedance, we already know that this is a cascode, and I'm interested to see the resistance from here. In that case, I'll start from here. Resistance looking from here is RO2, and the overall resistance looking from here is GM2 RO2 RO1 plus RO1 plus RO2. However, we can approximate same. Okay, I made mistake here. It has to be GM1 RO1 times RO2. And look at this, like this ratio GMRO is generally 18 to 20 volt per volt, or 18 to 20 as intrinsic gain of any transistor for technology. So it's 18 to 20, whereas this is in something in kilo ohm. RO2 is in kilo ohm, sometimes like 2 kilo, 10 kilo, depends on technology. So in that case, this is 20 times what we were achieving in the normal kind of current mirror, where we were achieving only source impedance as RO and the V minimum as VDS set. So here we got ZS equal to, or let's make it approximated value, equal to GM1 RO1 times RO2. Let's keep this one aside and let's forget about this, because it's better to remove this so that we can do the next analysis, which is finding out the V min. For V min, we learn that the gate potential, or the VGS, is equal to V on plus VTH. This is what we agree, where V on is nothing but VDS set, or the overdrive voltage. So in that case, from here to here, which is VGS, you're going to have V on plus VTH. We can name it V on 2 plus VTH. Subtracting 1 VTH from this quantity is going to give me the overdrive voltage across M2. Now from this point to this point, from here to here, it's equal to V on 1 plus VTH, because that is VGS, right? So in that case, that is what available here. Now let's hold a multimeter in your hand. One goes positive, goes here, and this one goes here. So you have the multimeter. So what you are going to see here, you are going to see effectively there are two voltages from here to here. One is from this point to this point, which is actually V on 1 plus VTH. Look at this point is V on plus VTH, and another one which is actually here, it's V on 2 plus VTH, right? Let's assume that V on 1 and V on 2 are equal, and that is what we are going to do with. We are not going to make multiple V on, because our main practice is, let's keep V on equal to, or we can make V on 1 equal to V on 2 equal to some number more than 250 to 300 millivolt, or maybe much higher than that one. It's depending on your requirement. However, sticking to the lower end, 300 millivolt, that's the V on 1, V on 2, and let's name them as V on, or in other book it's written VDS set. So any one of them you can write. So the multimeter which you are holding here, you are going to have 2V on plus 2 VTH as voltage over here from this point to this point. Interestingly, you can consider this big transistor M1 and M2. Let's combine them together and consider that this is a drain potential, same as this one, and this is a source potential, same as this one, and this is ground. And this transistor is combination of M1 and M2, whose gate is connected to the higher potential, which is 2V on plus 2 VTH. Then at the drain side, I'm supposed to see 1 VTH lesser than what is available. So that is going to be equal to 2V on plus VTH, where notably V on is nothing but VDS set or the overdrive voltage, right? So here you are achieving 2V on plus VTH. Look at this. This is very interesting because if you are achieving V on across M2, then to fulfill the KVL, this has to be V on plus VTH. Look at this. This is not just V on. Maybe by theory you must have thought that it is required just V on, but it's not V on, right? So across the cascade current, you don't require 2 V on or the 2 VDS set, but you need 2 V on plus VTH, so that both the transistors are in saturation, and this will make sure that it will have the same current of I or maybe double triple depending on what WL you are taking, right? So going into this, like this is already given in my slides, and you can see that it's coming around 2 VDS plus VTH across this one. So summarizing today's lecture, that we made two current mirror. One is a simple current mirror using a single transistor, and another one we have studied, it's cascade current mirror, and we evaluated which one is good because we have only two evaluation parameter. One is called source impedance and one is called minimum voltage. So in the case of simple current mirror, this is becomes R0, and this one is V on, or you can also call it VDS set, or you can also call it V overdrive volt, right? All are synonyms of each other. But in the case of cascade current mirror, ZS is GM times, like GM1 times RO1 times RO2. If both the ROs are same, then it's, and GM1 equal to GM2, then GM times RO square. And minimum voltage, as we found out from the developed theory, it's 2V on plus VTH, or you can also write down 2 VDS set plus VTH, or again you can write down 2V overdrive voltage plus VTH. So here you can see that the impedance wise it's good, no problem, but the V minimum potential is actually much higher than what is required. So if the regular one is like this is the regular current mirror whose current and VDS and ID are plotted like this. Then in the case of cascade, you're going to see something like this. So its impedance is improved, however V mean has not improved. This is in the case of regular, this is V on voltage. For this case it's 2V on plus VTH. For the case of regular, this impedance is 1 by R0, and for the case of Cascode, it's 1 by gm rho square, right? So that makes sense, right? So you have to find out the trade-off, and there are lots of things you need to take care while doing the design. Maybe we can talk about that in the next lecture. Okay. Okay, thank you very much for today.